Hello everyone. Many of the problems we'll go over today are indefinite integrals. In other words, there is no definite interval from a to b we're evaluating these integrals on. The result is just a general function. You may recall from last class we saw the following integral, and I presented you with an alternative integral and asked you whether you'd rather do that one instead. Because this one was a bit of a stretch, that's the purpose of today. We're basically doing reverse chain rule. And we're going to do so many examples together today that you'll get the hang of it soon enough. So when you encounter some of these more complicated integrals, our plan B approach is going to be substitution. Now this requires a bit of intuition, but it's fairly straightforward once you get the hang of it. So with this first one, I'm going to substitute x squared plus 1. So I will do u equals x squared plus 1. Now du with respect to x would give us something like this. And you can see that 2x dx appears in the integral as well. So if I replace x squared plus 1 with a u, I would get something over u. And because 2x dx is equal to du, I can just replace the integral here with 1 over u du. And the integral of 1 over u is just ln of u plus some constant. So because we're not evaluating it from some interval from a to b, for example, we need to include this constant. And now we can sub back in our expression for u, and we can write ln x squared plus 1 plus c. So let's try another one. 4x cubed plus 6 might not be a bad thing to substitute. Let's try that and see where it takes us. And then du would be 12x squared plus 0 dx. And I can see an x squared dx term here, but it's not a 12. So what we can do is maybe factor a 4 out of this. So we would have du equals 4 times 3x squared dx. So that means 3x squared dx is equal to du over 4. So now this integral would become 1 over 4. U is in the bottom. I replace it with 4x cubed plus 6. And 3x squared dx is equal to du. So that's my new integral. And again, the integral of 1 over u is just ln of u. So I can go 1/4 times ln of u plus c. And if I like, I can distribute this 1/4 into each of these things. Now because c is a generic constant, 1/4 times c, I could call that still another generic constant. So I could write this as 1/4 ln 4x cubed plus 6 plus c. So let's try another one. I'm going to try again substituting the denominator because that seemed to be working for me the last couple times. So I'll substitute cos theta, and then du would be negative sine theta d theta. So I see a sine theta d theta, but the negative is missing. So basically what I can do is say sine theta d theta equals negative du. So this integral would become negative over u. And then sine theta d theta I established was du, so du. And this integral is pretty easy to do. It's just ln of u. So it'd be negative ln of u plus c. And I can put the u back in and express it in terms of theta. So this would be negative ln of cos theta plus c. Let's try a few more. So this one's a little bit different. If I were to try to sub x for u, well, du is just dx, and there's no way I can get the ln taken care of in this substitution. So we need to try something else. If we try substituting ln x, du is 1 over x dx. So this integral will become u, and then 1 over x dx is equal to du. So it's just u du, and that's really simple to do. So u to the 1 would go to u to the 2 divided by 2 plus c. And now I can put ln x back in for u. So ln x squared divided by 2 plus c. So hopefully now you're starting to see the types of substitutions that make sense. For this one I'm going to substitute 4 theta. So du will be 4 d theta. So I can see a d theta come up, but I don't see a 4. So if I divide both sides of this equation by 4, that would be what we need. So du over 4 is equal to d theta. So the integral will become 1 over 4 sine of u du. And we can continue to ask ourselves, where did this derivative come from? So it would have come from a negative cosine. So we would have negative 1/4 cos u plus c. And I can substitute 4 theta back in here and get it in terms of theta. So negative 1/4 cos of 4 theta plus c. So with this next one, if you try to picture where this derivative came from, if you did the derivative of sine x, or 2 plus sine x as it is here, that would give you a cos x term. So it would probably make sense if this came from something to the 11th power. So we can try substituting that. So u equals 2 plus sine of x, and then du would be cos x dx, because the derivative of sine is cos. And from there, it's a really easy replacement. We can see cos x dx, and 2 plus sine x is just u, so the integral will become u to the 10th du. And this derivative would have come from u to the 11th divided by 11 plus c. And we can sub back in for u, so we would have 2 plus sine of x to the 11 times 1 over 11 plus c. So we'll do a few more. With this one, it actually seems like we have a couple options. We could try subbing e to the root x, and then du for this would be e to the root x, because the derivative of e is itself. And then we need to do chain rule with this, so that would be 1 over 2 root x, and then dx. So du seems to cover the entire integral, except we have a 1/2 here as well. So we could replace this integral with 2 du. And the derivative of du would just be u, so we'd have 2u. And we know u is e to the root x, and we'd also have to have a constant. So this should be 2e to the root x plus c. So that's one way to do it. There's another approach though. We could go with root x, and du would be 1 over 2 root x dx. And our integral here would become e to the u, and 1 over 2 root x dx is equal to du. So we could just replace basically all of 1 over root x dx up here with a 2 du. So we could take this 2 outside, and then the integral of e to the u is just e to the u. So we'd have 2 e to the u plus c. And we can sub back in for u, which in this other way of doing it is root x. So we have 2e to the root x plus c, which is the same result as the one we did before. So that doesn't always work, but it's nice to know that you can do it a few different ways sometimes. Other times you might have to pick something different. If your first choice doesn't work, try something else. So with this one, the logical choice might be 15x cubed plus 7. So let's try that. 15x cubed plus 7. And then du would be 45x squared dx. And we have an x squared dx in our original integral, so we can replace x squared dx with du over 45. So our integral would become 1 over 45 root u du. Or if you prefer, 1 over 45 u to the 1/2 du. So next we can add 1 to the exponent and divide by that same thing. So 1/2 plus 1 gives 3/2, and we'd have to divide by 3/2 as well. So the result of this integral would be 1 over 45 u to the 3/2 divided by 3/2 plus c, which is basically 1 over 45 times 2/3, which would give us 2 over 135, and we can sub u as 15x cubed plus 7, 15x cubed plus 7 to the 3/2 plus c. So we get another indefinite integral here. We could try maybe subbing x ln x. Why not? Let's see if it works. X ln x. So in this case, du, we would need to apply product rule. So the derivative of the first times the second would give us ln x, plus the derivative of the second, 1 over x, times the first, which just gives 1. And then that would be dx. So there's no real obvious way I can work with this with the original integral, so it looks like we might need to pick something else. We could try ln x. So ln x and then du is 1 over x dx. And that required some intuition because I see a 1 over x term here, and I know the derivative of ln x is 1 over x. So that seemed like a safe choice. Now the only thing unaccounted for here is the 3. So that's fine, we can pull that out front, and the integral would become 1 over u du. Because I've replaced ln x with u, that's taken care of. I pulled that out front, and 1 over x dx is equal to du. Now the integral of 1 over u is just ln of u plus c. And we can put ln x back in for u, so we would have 3 ln of ln x plus c. So we'll do a couple more indefinite integrals, but first, in general, using substitution undoes the chain rule. So you can see a bit how this works. So on to the next one. The obvious choice here might be 2x minus ln x. So we can sub u equals 2x minus ln x, and then du is equal to 2 minus 1 over x. So it looks like we've got everything accounted for. We've got 2 minus 1 over x dx, and we've got sine of u. So our new integral will become sine of u du. And sine would have come from a negative cosine, so negative cos u plus c. And we can substitute u back in here, 2x minus ln x. So minus cos 2x minus ln x plus c. All right, one more and we'll let you try one. So for this one, 3x squared plus x seems like a reasonable choice, because if I do that, 3x squared plus x du is 6x plus 1 dx. And I don't quite have 6x plus 1 here, but if I factored out a 5, I would have 6x plus 1. So it looks like we got it covered. So we can pull this 5 out front, and then we have e to the u, and then we would have 6x plus 1 dx, which is equal to du. And the integral of e to the u is just itself, so we have e to the u plus c, and we can just put 3x squared plus x back in here. So then we have 5e to the 3x squared plus x plus c. So I'll leave this one for you, and this should be the result. So now we're going to do a few definite integrals. So the strategy is the same. We're going to substitute something, but now we have upper and lower bounds to account for. So with this integral, I might choose 1 plus 2x cubed to substitute, and then du would be 6x squared, which is nearly what we have here. We've got an x squared dx. So then du divided by 6 would be x squared dx. But now we need to adjust our interval because the lower and upper bound for this integral was based on x. We need to adjust it for u. So when x is 0, I would sub a 0 in there. So 2 times 0 cubed plus 1 is 1. So when x equals 0, u equals 1. And then for the upper bound, 1, when x is 1, 2 times 1 cubed is 2, plus 1 is 3. So when x is 1, u is equal to 3. So now this integral would become 1 over 6 u to the 5th du, with my lower bound 1 and my upper bound now 3. And u to the 5th would have come from a u to the 6 divided by 6 plus c, and we need to evaluate that from 1 to 3. So I could factor a 1 over 6 out from here, giving me 1 out of 36 u to the 6 plus c. And again, if I factored a 1 out of 6 out of this term, that would just give me another constant, and I can just call that c again. So we have 1 out of 36, and then we would do 3 to the 6th power, which is 729, plus c, and then we would subtract 1 to the 6th plus c, so that would be 1 plus c, and c minus itself is 0, so we would have 729 minus 1, which we would have 728 over 36, which reduces to 182 over 9. So we'll do one more definite integral together. So we could maybe substitute ln x here, try it out. and then du would be 1 over x dx. So it looks like I've got most of it accounted for. I've got 1 over x dx here. I've got an ln x. So if this were an indefinite integral, I would just have 1 over root u du. But now I need to adjust my limits of integration. So when x is e, if I put an e in for x here, the natural log of e is just 1. So u is equal to 1 for the lower limit. And when x equals e to the fourth, if I put e to the fourth in here, that would give me 4 for u. So my new limits of integration are from 1 to 4. So if you like, you can think of 1 over u as u to the minus 1/2. And to get the integral, we would add 1 to this exponent and get something and divide by that same thing. So this would be 2 times u to the 1/2 plus c from 1 to 4, which would be 2 times 4 square rooted is 2, and then the c wouldn't really matter, it just goes away. And 1 to the 1/2 is 1. So 2 minus 1 is 1 times 2 is 2. So I'll leave it up to you to prove that this one is equal to 0. And I should also introduce you to a handy tool if you don't know about it yet. It's Wolfram Alpha. So you just search Wolfram Alpha in a browser of your choice, and you have a field here to do whatever you want basically. And the nice thing about this site is it does it symbolically. Unlike your calculator, unless you have one of those fancy ones, which just does it numerically. So by the way, if you want to do an integral, you just type integral and then type your function. So we'll do 2 more together. These are slightly different than the ones we've just done, so it's worthwhile to go over them. So with this one, we can substitute x minus 4, and then du is equal to dx. Now unfortunately, it looks like we don't have the whole thing accounted for with this arrangement. We just have 1 over u, and there's an x that's unaccounted for. So what we need to do differently here is let x equal u plus 4. So then our integral becomes 1 over u, and then x is u plus 4, and then dx is equal to du. So that's it. And we can split this up. So this would be equal to u over u plus 4 over u du. So we can simplify this a little bit further. U over u is 1, so that's just du. And we can add 1 over u du. The integral of du is just u, and the integral of 1 over u is ln u. So we have 4 ln u. And then we need to have a constant because this is an indefinite integral. So now we can just sub x minus 4 back in for u. So we have x minus 4 plus 4 ln x minus 4 plus c. And this constant can absorb the minus 4. So we would have x plus 4 ln x minus 4 plus c. So this constant has just absorbed the minus 4. So I've basically done constant minus 4 equals some new constant which I haven't changed the symbol for. I'll leave the one on the right there for you to do and prove that the result is negative 8 ln 6 minus x plus c. It's a very similar substitution to the one we just did. So now onto this one. We could maybe try substituting u equals x plus 1 squared. Now that would give us equivalently x squared plus 2x plus 1, and then we'd have du equals 2x plus x. And unfortunately I don't really see any way we could square that with the original integral, so it might be a good idea to pick something else. Let's maybe try x plus 1 instead. So that means du equals dx. And it looks like we've missed some stuff, so we would have 1 over u squared, which is great, but we have an x unaccounted for. So we would need to solve for x in this equation. X equals u minus 1. So our integral here would become 2u minus 1 over u squared du. And I can split this up a little bit. So this would be 2u over u squared minus 1 over u squared du, which would be equivalent to 2 1 over u du minus 2u to the minus 2 du. So 1 over u is just ln of u, so 2 ln u. And then we would be subtracting 2, and u to the minus 2, we would need to add 1 to the exponent here. So negative 2 plus 1 is negative 1. And we need to divide by that same number. So we would have u to the negative 1 divided by negative 1. And we need a constant in there as well. So I guess finally we would have 2 ln of x plus 1 plus 2 over x plus 1 plus c. So I'll leave this one for you to do as well. It's not as easy as the other one on this page, but I'll give you a hint. So square root of u times u plus 1, you can distribute this in like that. And that's probably the crux of the integral, and I'll leave it to you to prove that this is the result. So you can also try this one as well if you like, but you could finish the ones I've indicated in the video so far. And that's it from me for today. I'll see you next time.